Laser powder bed fusion has matured rapidly over the past decade, yet most process optimization still revolves around familiar variables such as laser power, scan speed, hatch spacing, and layer thickness. If you have ever observed two parameter sets with identical energy density producing completely different melt pool behavior, defect populations, or residual stress states, the underlying reason is often not power or speed, but the shape of the laser beam itself. In this video, we will explore how laser beam physics directly governs melt pool stability, thermal gradients, and final part quality, and why beam shaping is emerging as a practical and powerful control lever for industrial metal additive manufacturing. In most commercial LPBF systems, the laser delivers energy through a Gaussian intensity profile, where the highest irradiance is concentrated at the center and decays radially outward. This energy concentration has significant physical consequences during melting. The sharp central peak of a Gaussian beam drives extremely high local temperatures, steep thermal gradients, and strong vaporization effects. These conditions intensify recoil pressure, promote spatter, and increase the likelihood of transitioning from stable conduction mode, melting into unstable keyhole behavior. Beam shaping fundamentally alters this interaction by redistributing energy across the beam cross-section. A top-hat beam delivers energy uniformly, a donut beam removes energy from the center entirely, and a Bessel beam combines a narrow central peak with surrounding rings. These differences change not only how metal melts, but also how heat flows, how fluid moves inside the melt pool, and how the material ultimately solidifies. Despite these physical differences, beam shapes are often compared using linear energy density, LED, or volumetric energy density, VED. The implicit assumption is that if two processes share the same energy density, they should behave similarly. However, this assumption breaks down when beam shape changes. Energy density describes how much energy is delivered per unit length or volume, but it provides no information about how that energy is distributed spatially across the laser spot. Two beams with the same power and scan speed can therefore deliver very different total intensities to the material, leading to fundamentally different melt pool behavior. As a result, relying solely on LED or VAD can obscure the true influence of beam shape and lead to misleading conclusions during process optimization or parameter transfer. To resolve this issue, an intensity factor, denoted as beta, can be introduced to account for the total absorbed intensity of a given beam shape relative to a Gaussian reference. When LED is multiplied by this factor, the result is a corrected metric known as LED star. This correction ensures that different beam shapes deliver equivalent total energy to the material, allowing their effects to be compared fairly. By normalizing energy input in this way, it becomes possible to isolate the true role of spatial energy distribution without conflating it with differences in total intensity. From an industrial perspective, LED star provides a more physically meaningful framework for benchmarking processes, transferring parameters between machines, and evaluating productivity claims associated with alternative optical configurations. Once energy input is normalized using LED star, a key observation emerges. Across Gaussian, top hat, donut, and Bessel beams, the melt pool width and depth become remarkably similar. This finding reveals that melt pool size alone does not capture the full story. While geometric dimensions converge under equal total energy input, the internal thermal state of the melt pool remains highly dependent on beam shape. Differences in peak temperature, temperature gradients, and thermal uniformity persist, and these differences ultimately govern stability and defect formation. When temperature fields are examined directly, the influence of beam shape becomes unmistakable. Gaussian beams generate the highest peak temperatures and the steepest thermal gradients, often exceeding vaporization thresholds at the melt pool center. Top hat beams, in contrast, produce lower peak temperatures and a much more uniform thermal field, keeping the process firmly in conduction mode and reducing instability. Donut beams moderate central overheating while maintaining adequate penetration, leading to improved melt pool stability. Bessel beams exhibit behavior that depends strongly on interaction time. At low scan speeds, the central intensity peak enhances penetration depth, while at higher scan speeds, reduced exposure time causes the beam to behave similarly to a donut profile. These thermal differences directly influence Marangoni flow, spatter formation, and keyhole susceptibility. Viewed collectively, each beam shape presents a distinct balance of benefits and limitations. Gaussian beams offer strong penetration but suffer from high peak temperatures and a narrow, stable processing window. Top hat beams provide the most stable thermal conditions, enabling higher energy input without instability. Donut beams strike a balance by reducing central overheating while preserving melt pool continuity. Bessel beams enable deeper penetration under appropriate conditions, but their effectiveness depends strongly on scan speed and interaction time. Understanding these characteristics allows engineers to select beam shapes based on process objectives rather than treating optics as a fixed constraint. From a practical standpoint, beam shaping becomes a decision tool rather than an abstract concept. When stability and repeatability are the primary goals, top hat beams offer clear advantages. When higher productivity is required without triggering keyholing, both top hat and donut beams expand the usable processing window. In applications requiring increased penetration depth, Bessel beams can be effective at lower scan speeds. Even when limited to Gaussian optics, awareness of these physical mechanisms helps engineers manage risk by avoiding parameter regimes that drive excessive central irradiance. Beyond immediate process stability, beam shaping also influences residual stress and microstructural evolution. Thermal gradients dictate cooling rates and solidification behavior, which in turn affect grain morphology and stress accumulation. Gaussian beams promote steep gradients that favor columnar growth and higher residual stress. More uniform profiles, such as top hat beams, flatten thermal gradients and create conditions more conducive to equiaxed microstructures and reduced stress. This demonstrates that beam shaping provides a non-compositional route to microstructure control, complementing alloy design and post-processing strategies. Taken together, these results demonstrate that beam shape is as influential as power or scan speed in determining process outcomes. Standard energy density metrics are insufficient when beam shaping is involved, whereas LED star provides a physically grounded alternative. Melt pool dimensions alone do not guarantee stability, as internal temperature distributions play a decisive role. By redistributing energy more effectively, beam shaping expands the stable processing window and enables higher productivity without sacrificing quality. As metal additive manufacturing continues to scale toward higher throughput and stricter quality requirements, beam shaping is transitioning from a research topic to an industrial necessity. Engineers who understand how spatial energy distribution governs melt pool physics gain a deeper level of control over defects, microstructure, and performance. Mastering beam shaping is not simply about refining parameters, it is about fundamentally improving how energy is delivered to the material. If you found this breakdown useful, support the channel by subscribing for more practical insights into metal additive manufacturing. Thank you.